In this video, we will talk about a special type of kinematics that is special not because it's any more difficult, but just because it is ubiquitous. It's something you will encounter in any introductory physics course, so let's make sure we know how to do it in ours. I'd like to start by reminding you what the law of inertia is, which is that objects do not experience any delta V unless they interact with another object. And I said we're going to get into a little bit more detail about that in the future. But for now, what I want to point out is that means if an object is experiencing a delta V, it's interacting with another object. Despite what Wile E. Coyote experiences right here, where he runs out, then notices he's going to fall, and then falls, in reality, we do experience delta V when an object is dropped or when we fall. We experience that right away. And I want to point out, gravity is not an object. If you say that Wile E. Coyote is falling because of gravity, that's fair, that's valid. But the object that's causing him to fall is the planet Earth. The planet Earth is pulling down on us at all times, and if circumstances are right, meaning nothing is supporting you, then you can fall. And gravity is how the Earth pulls down on us. And again, we will get more into that in a future chapter. But for now, what I'd like to talk about is how we respond, or how objects act when Earth is pulling on them gravitationally, just in terms of the kinematics. And the kinematics works like this. The more massive an object is, the more inertia it has. So we saw in the previous video, or one of the previous videos, that I was pushing that little red cart. We talked about what if the cart was 6 times more massive. It would have 6 times as much inertia. So for the same push, I would have given it a much smaller delta V, and it wouldn't have had as much effect. That's what we're talking about when we say the more massive an object is, the more inertia it has. However, the more massive an object is, the stronger the pull downward by Earth. So unlike me pushing the cart, where we're talking about the same amount of force acting on a more massive object in that hypothetical scenario, when it comes to an object in free fall, a more massive object is harder to accelerate, but the Earth pulls down harder on that object. And the net result is that all objects will fall in vacuum at the same rate. A really massive object and a not so massive object, they'll each fall at negative 9.8 meters per second per second. The negative means that objects that fall are falling downward. So if you leave it off when you're talking about it, it's not really confusing. If you leave it off in your math, it can be very confusing. This image here is a little cartoon of someone dropping a heavy object and a light object off the Leaning Tower of Pisa. It's probably not true that Galileo did that, but it's probably true that someone around the time of Galileo did that, and it was pretty related to the type of work Galileo was doing. And so a lot of times people will say that Galileo proved that objects fall at the same rate. And that's true that objects fall at the same rate, and historically it's a little sloppy, but I'm not going to ask you about the history of it. If you want to know about objects, back up to this one. I said if they're falling in vacuum, they fall at 9.8 meters per second per second. That means if there's no air resistance. If you drop a feather, you'll find that it doesn't fall as fast as a rock. And that's not because gravity is different. It's because the feather catches a bunch of the air on the way down and it slows it down like a parachute would. For this course, we will neglect the effects of air resistance whenever we're talking about dropping objects. If you want to know more about air resistance, you can either talk to the aerospace engineers that are out there, or you could take some upper level physics classes. But for now, we just want to focus on the fact that making an object heavier doesn't change how fast it falls. Okay. This slide is here to talk about something that's very important, very useful when we're talking about an object that has been thrown upwards, and that is that there is symmetry in free fall. Free fall is just a term that means that an object is not in contact with anything. It's not propelling itself in any way, and that gravity is the only thing that is influencing how it's moving. So the Earth pulling on it gravitationally is the only thing that's influencing how the object moves. Symmetry is very important for an object like that Because if you consider throwing an object straight up in the air and then it's allowed to fall back to the same height that it started from, clearly the distance it travels upward is equal to the distance it travels back downward. And if it has the same gravitational acceleration the entire time, we could do the math to prove this if you're not convinced, but it takes the same amount of time to go up as it does to come back down. So that means that at any 2 points on the arc, the object will actually have the exact same amount of velocity upward as it does downward. For example, at this height right here, the velocity that it had when it was going up right here is equal to the velocity that it has when it's going down right here, except that one of them is positive and one of them is negative. This symmetry is very, very helpful, because if you tell me that you throw the ball at 13 meters per second and then you catch it right here at that same height, I know that you caught it at a final velocity of negative 13 meters per second, even though the question didn't say that. I also know that if the ball was thrown vertically upward, then when it reaches the very top, it has stopped moving up and will start coming back down. So for a brief moment here, its velocity is 0. That means I could break this problem up into a goes up part and a goes down part, or I could try to do it all at once, where V initial is plus 13 meters per second and V final is minus 13 meters per second. We'll do several of these, and I'll try to do several examples of these, because there are places where this comes across a little bit tricky. But it's not that it's hard, it's that it's a little bit tricky, which means once you've had a chance to do these problems a few times or see them done, it tends to be not too bad. This slide is here to emphasize that what we just talked about on the previous slide, what's happening is only mathematically symmetrical if it is physically symmetrical. So if you throw an object straight up in the air, and when it comes back down, you don't catch it at that same height, and you allow it to fall, say, to the ground or down past your hand all the way down this long cliff, that problem will only be mathematically symmetrical from up to down here. And then after that, it's not. So if I tell you it takes 1.3 seconds to cease moving upwards, and then I ask you how long is it falling downwards, the 1.3 seconds up tells me that it takes another 1.3 seconds to fall down to here. But then it takes more time to continue falling down past that. And how long the total trip is, I would need to know more information about how far it falls. Also keep in mind that an initial velocity for my object, when I throw it vertically, I could be throwing the object straight upward. I could also be throwing it straight downward, and you'll want to pay attention to that. If it's thrown straight downward with a velocity of 13 meters per second downward, then that's a negative 13 meters per second. This is where that negative 9.8 meters per second acceleration due to gravity will potentially get people mixed up if they're not careful about that negative. You need to know that the acceleration due to gravity is causing an object to slow down if it's traveling upward, but to speed up if it's traveling downward. So please be careful with your negative on that. That's everything for free fall problems in one dimension, and we will deal with two-dimensional kinematics and projectile and free fall problems after our first test.